Hello, everybody. My name is Hamid. I'm the product architect for the geophysics tools in the GeoGraphix suite. For today's presentation, I will be taking you through the basic workflows required for a seismic interpretation in GVERSE geophysics. GVERSE geophysics, of course, is the seismic interpretation package for GeoGraphix. We are fully integrated with the rest of the suite. And there's a lot to cover today, so this will be more of a high-level walkthrough because we just, every workflow that is a requirement for seismic interpretation. There's possibly no way I can go through all of them within this hour and a half time frame that I have. But these are some of the things that I'll be talking about today. I will start with how we manage and load data, talk about some of our visualization tools to help you view your seismic and associated data, associated subsurface data. We'll look at how we create synthetics, and then your basic horizon and fault interpretation, followed by a Geobody interpretation in GVERSE geophysics, and a few words on our depth conversion workflows. All right, so let's get to the demo, and this is where you'll mostly start your day, the Project Explorer. To interpret your seismic, you must first create what we call a GVERSE geophysics interpretation. You can think of an interpretation as a mini geophysics project within the main GeoGraphix project. It is basically a container, and all data that you create during your interpretation or you bring in to assist your interpretation is stored here. So your horizon picks, fault sticks, velocity models, everything is saved as part of the interpretation. And you can have many interpretations in a single project. As you can see in this particular project, the F3 block 2019.3 project that I have activated over here right now, I have a few different interpretations available already in this project. So you can have many interpretations in a single project, and these interpretations can access data between one another too, using a tool that we call the interpretation browser that lets you copy data between interpretations. The interpretation contains all data that you create or consume as you interpret your data. That is all data except for the seismic itself. That's because seismic files tend to be very large. We don't want you to create unnecessary copies of these big files. So the interpretation stores only a pointer to the seismic file. And many different interpretations can point to the same file. So different interpretations can use the same seismic file if it's the same area that you are working in. You can, of course, work with 2D or 3D seismic. You can have a large 2D project or a multi-survey 3D project or a combination project with both 2D and 3D data. Our architecture is 64-bit, which basically removes any memory restrictions. So you can work with these very large regional scale projects with lots of 2D and 3D data, or with prospect level single 3D surveys, or even a single 2D line if you want to. We store the seismic in a brick format. Our SegY loaders take SegY data, which is conventionally the format seismic data is transferred in, is stored in. So our SegY loaders take the SegY data and convert it to our own format, which is a brick format, and which essentially means that because the SegY data is not optimized for visualization, we convert it to our format so that you can view that data a little faster, much faster actually. Not just a little faster. The loader itself is an easy wizard-based interface and can handle most commonly encountered scenarios without much difficulty. So now I'm going to switch to an actual interpretation. You should be seeing a map with some 2D and 3D seismic on it, a time structure map of a horizon, of polygons, some wells. So this is, when I open up an interpretation, this is what it's going to look like. This is called the main map view. In the interpretation, when you add a 3D seismic file to it, we first create what we call a 3D survey, and that's what you see here. This is a 3D survey that I've added to this interpretation using my interpretation manager, and I'll get to that in just a little bit. But before I show you the interpretation manager, I want to tell you how we actually work with seismic data. So how does the interpretation see the seismic data? The survey that you see on the map is just the geometric information, your X and Y, inlines, crosslines, their increments, basically where you are in the world and what your survey looks like. How do you define your survey? And that is what you see on this map here, the 3D survey. The trace data itself, the actual seismic, we associate that with the survey as a data version. So if I go to my interpretation manager, you can see that for this 3D survey called the F3 original, I have 4 different versions, data versions associated with it. So if you have attributes computed for the same survey or different processing parameters or whatever the reason may be for having multiple trace files for that same survey, you can add them to your interpretations as data versions to the same survey. Same thing for 2D lines. For us, the line itself, this line itself here is just the geometric information. Trace data is stored as versions associated with this line. In this interpretation, in this example, I just have a single version of data associated with all of these 4 lines, but you could have multiple versions of data for each 2D line as well. The only difference from the 3D survey or the management of our 3D seismic is that we have an additional layer of organization called programs. So you can see I have 2 programs. One is called dip lines, the other is called strike lines, and this is purely an organizational methodology. You can add multiple lines to a single program. That is completely up to you, how you want to organize that, create multiple programs. This helps in making sure that if you have a lot of 2D lines that you're working with, this will make sure that you have a handle on how they're organized within your interpretation. All right, so well data. So you can also bring in well data to assist with your interpretation. Now this GeoGraphix stores all its well data in a module that we call well base. Well base is a play on the words wells and database. So it's essentially a database containing all of your wells. All of the wells that are in the project are stored in well base. Now, because we are integrated in fully with the suite, we are part of the suite, an important part of the suite, we can talk to this well database, well base, and get that well information that we require. And this is a live link, so any changes that you make in that well using any of the geology tools or petrophysics tools, those changes will be reflected in your interpretation as well, in your seismic interpretation as well. But we don't force you to use all the wells in your project. Many of our users work with hundreds of thousands of wells that are available at any given time in their well-based database, and you may not always need all those wells when you're working with seismic. You need a specific subset of those wells. You can choose to bring in a specific subset of those wells into your interpretation, so you're only working with wells that you need, and eliminate on the noise a little bit. Like I said, even though you're bringing in a subset, it is still a live link. You can always add more wells, remove wells, and whatever changes you make here or in other tools, those are all updated in real time with the database. So information is available across all applications in the GeoGraphix suite. So that's how you bring in your data, and once you have your interpretation set up, you open it up to get this main map view, your base map, where you're viewing everything that's important in your data sets. You can of course configure this, you can hide and remove things, you can change colors, all that stuff. All right, so now once you have your data in, once you have everything loaded up, next step would be to obviously visualize your data, to see it, to see what you look like, identify things that you might want to pick or ignore and stuff like that. So of course you want to be able to view your seismic, view your horizons and all that stuff. To open a seismic line, you interact with this map. You just choose this button here. Let's open this particular inline right here. Just click on the map, and that's going to open in what we call the seismic view. This is like an interpretation view. It gives you just a flat view or a vertical view in this case for your inline of 444. You can see that in the top of the window over here. The data itself is basically displayed right here. The seismic data, any wells that this line intersects, this particular cross-section intersects, are displayed as well bores. You can also post other data on the wells. So I have my formation tops posted here. I have a synthetic or log. If I want to view a synthetic trace or a log curve trace, I can view those here as well. You can play with these display settings. So if you want to maybe view your wiggle traces on here as well, turn them on, and that's going to display wiggle traces on this particular section. Let's just turn it off for now. settings, trace display, turn off my wiggle trace. And of course annotations, if you know how far apart you want these timing lines to be, all that stuff is configurable from the Seismic display window. You can also control what your wells look like. So if you want to change the color of your well core, what data you want to post on it, all that information again can be configured using the Seismic display settings tab. If you want to change the color palette, so right now by default I'm getting a red, white, black color palette, but if you want to change that for this particular window, for this particular view, you have the color bar over here, and right under that you have the settings option that lets you choose from a lot of predefined color palettes. You can also edit these color palettes to go in and get the colors to represent exactly what you want them to represent. So that's and of course when you view a seismic section, all the horizons and any faults and all that stuff are also displayed on here. So you might be able to see these colored lines going through here. That of course are your horizons that I picked. If you had any faults in there, they would also show up on this section automatically. So you don't have to add them in this view to be able to see them. We also have a very good, very versatile 3D viewer to view the same line in the 3D section. You could either open it from the map in the 3D view, or you could just right click on the section and say, I want to view this in 3D, click on this, and that's going to add that to your 3D viewer. Now I can look at that same inline 444 in the 3D view. You can see it's the same inline 444 comes up in the 3D view. Before we go on a comment about the 3D view, the interface looks very different. This has got a much more modern look and feel to it. We have a ribbon-based interface up here, tier away tabs, so you can take this tab and move it to another screen or dock it anywhere in the application where you want to. So if you have multiple views, because you can do multiple 3D views at the same time, and you want to dock them right next to the other, to all of that. But the important point to note here is that even though the map view, the section view, they look very different from the 3D view, they are still the same application. So they access the same files, access the same memory in the RAM, even so. You can think of them as two different views of the same data. And since they modify the same file and the same memory space in your RAM, you don't have to worry about pushing and pulling data between the two apps to keep them in sync. That's inherent to the two views because, like I said, they are still the same application. Also, once you are in the 3D view and you want to add more sections to it, because obviously you just don't want to look at one section for your analysis, you want to be able to add more inlines, crosslines, time slices. We don't expect you to switch back and forth between the map views and this view to be able to add more section. Up here in the ribbon, I have these options which can let me graphically choose and put data in my survey, open different lines in my survey. So if I want to open a cross line, I can just select this cross line option, and maybe this bright amplitude is something I want to investigate further. Right click here, and now I have this cross line added to my scene as well, where I can now look at the same seismic data displayed on that cross line. Time slices also, if you want to add time slice, you can just graphically point to where you want to add this to, or if there's something interesting that you want to see, maybe over here, just right click here and say open time slice, and that's going to add a time slice to your scene. You can also navigate this using this bar in the bottom. It lets you take this time slice and move it to other locations. You can grab your inline with the mouse key, move it with your mouse to wherever you want to put it to, and that's going to then navigate your section to wherever you want it to be. And it's not just limited to 3D seismic. Any other data that you have in the interpretation is listed here in what we call the interpretation tree. So I have all of my data versions available here, my 2D programs, all the lines in each program. So if you want to add this, view this 2D line, just click the plus icon. That's going to add that 2D line to the scene as well. So now I'm looking at my 2D line here as well. Horizons that you have already picked and you want to view, just add them to the scene, drag and drop, or click the plus icon. That's going to add the horizon. Same thing for faults. Just click on a fault and add that to your scene, and that's going to show up in the scene as well. So the interpretation tree and wells, of course. And if you click on this plus node next to a category node, it's going to add all those objects into the scene in a single click. So I have like these 7 wells. I want to view all of them in the scene. I click this plus icon next to the category node. That's then going to show me all the wells added to my scene. So you can add any and all data that is available in your interpretation to the 3D scene to look at what the whole thing is doing in a 3D sense. So this is the interpretation tree. Right next to is the scene tree, which describes the scene for you. It tells you what you have in the scene. So I have an inline, a cross line, a time slice in there, a 2D line, a horizon called top forest called A, and all of these wells in the scene. So it's a list of everything that I have available in the scene. Now, staying with visualization of seismic, I mentioned that we can, for a single survey, we can have multiple versions of data in there. So for example, if I go to my interpretation tree, you can see I have 4 versions of data available with this particular survey. And I can, of course, view any of these data versions. So if I want to view data from the average energy cube, for example, I just click on these labels in the scene tree and choose average energy, and that's then going to show me data from the average energy cube. Now I'm looking at data from the average energy cube. I'm just going to hide everything else so that you have a better view here. And you can configure these color palettes for these particular versions of data as well. So I go to my home tab, I say default color palettes. Right now I have the same palette set for everything. So if for my average energy, I wanted to show up maybe in rainbow palette, I'll just say rainbow here, and I know that for this histogram I want to set this to 0. Hit OK. So now whenever I look at my average energy data, it's going to show up in that rainbow color palette, and you can see that the color palette. So I can do this for any and all versions of data. So for example, semblance doesn't really make sense in black, white, red. Maybe it'll show up better in grayscale. So I just switch back to grayscale, click OK, and now whenever I open any section for the semblance volume, or let's just go to back to this time slice and switch this to semblance, and change this data version to semblance, that's going to then use the grayscale color palette, because that's the color palette that I choose for it. Now you can see that semblance data on that time slice in the grayscale color palette. So we have like full control over which palettes you want to use for your display. And this setting, of course, default color palettes, like all of our settings, applies to both the 2D view and the 3D view. So if I switch a section to the average energy volume or the semblance volume in the seismic view, in this view right here, that's going to use that same color palette that I choose over here. All right, one more thing before I move on is when I click on this label list, you might have noticed this last option called the active velocity model. But when I look at my list of versions, that does not appear as a data version, because this option works slightly differently. You can think of it like a virtual version. The active velocity model option, when I use this, it goes to my velocity model for this particular inline. It looks at the parameters of the model, figures out the velocities on this section, and then displays them over here. So it's like a virtual version, and it's not a trace file that's living on your hard drive like the other trace files that I have, or the other data versions that I have. And we have a variety of depth conversion workflows from the depth conversion tab in the 3D view, or the depth conversion menu on your main map or your seismic views. You can go in and you can create different velocity models and access all these different depth conversion workflows. Velocity models, we have several different kinds of velocity models that you can create and then use in your interpretations. The first one is called the horizon formation based model, where you can choose the horizons you want to use in your interpretation. Now, each horizon can be associated with the formation top in different wells. So for the horizons that I've selected, the time information, of course, is now coming from my horizon picks. We look at all the wells that this horizon sort of intersects. We look at the formation that is associated with that horizon, get the depth information from that formation pick, which gives us TD pairs at all well locations, and then we grid along that horizon using whatever gridding parameters you use down here to create a velocity model. Now, if your formations have multiple observations, so if you're working with horizontal wells and you have multiple observations for a single formation, you can choose to incorporate those multiple observations in there as well. If you made control points for your velocities, so if you have manually gone in and edited some velocity values and you want to incorporate those into your velocity model, you can do that as well. If you want to make sure that your gridding stops at fault polygons, that they're not sort of included or smoothed over during the gridding phase, you can choose to exclude rather those fault polygons from your velocity model as well. So that's how horizon formation-based velocity models work. Time information coming from your horizon picks, and depth information coming from your fault picks. Sorry, not your fault picks, your formation picks associated with those horizons, giving you TD pairs, and then you get your velocity model. And of course, you can do an average or an interval velocity model, whichever one you're interested in working with. The other option that we have is a structurally interpolated TD model. It works the same way. So you choose your horizons, and then you create TD pairs and grid it using these gridding methods down here. The only difference is the source of the depth value. In the horizon formation model, you're getting your depth from the formation picks. In the structurally interpolated model, instead of getting your depth information from the formation picks, you are getting it from the TD table of the well, the time depth table of that well. Because of course, seismic data is in time, you need a TD table to be able to draw wells or work with wells in the time domain. So we use that TD table to see where the horizon is intersecting that well, get that time value, look up that time value in the time depth table for your well, for each well that the horizon intersects, get your time depth pairs, and then grid along those pairs to get your structurally interpolated TD model. We also have a new type model that we've just recently introduced called the seismic velocity-based model. This is, so if you have your velocities in a text file, this could be coming from a processor or wherever else. It's just a text file that you have with velocity information. You can go in there and you can choose. You can define which if it's a CSV file, tablet delimited file, you can choose where everything is in terms of columns and bring that in, and we're going to build the velocity models using that information. This typically happens when you're working in a new area where you don't have a lot of information, so you're using those sort of unreliable velocities from your processor. So if you have some well control and you want to make sure that you incorporate that well information into this model as well, you can check on this option, say calibrate model with wells, and that's then going to use your existing wells, any wells that have TD tables with them, and it's going to sort of incorporate that into your velocity model as well. Other than that, we have a triangulated model. That's our default model. So even if you don't create any velocity model, we give you a triangulated model where we take all the TD tables for your wells that are in your scene, or rather in your interpretation, and we triangulate between them to create a velocity model for your entire survey. That's your default model. So you're always, as long as you have a few wells in your interpretation with time depth tables available with them, you're always going to have a velocity model. We can also use an external cube. So if you don't want to create your own velocity model, you have a segY file or a 3DX file with velocity information, you can just always use this external volume option, browse to that file. Then instead of creating a velocity model using parameters and figuring out those velocity values, you're just going to read the velocity values from the cube. So that's sort of like a pre-computed velocity model sitting on your hard drive, and instead of having to compute it every time you want to use it, you're just going to use the information from that cube. All right, so that's some of our velocity modeling options, how you can create those velocity models. Once you have the velocity model, you can of course export your time file as a depth file. You can convert horizons, create depth structure maps for your horizons. You can convert faults, geobodies, all that stuff. So everything that you associate with depth conversion. And also, this velocity model is used for integration with our geology tools. So if you want to view your seismic as a backdrop on your cross sections, you're going to convert that seismic from time to depth, because the cross section is always in depth. And seismic, usually in time, can also be in depth. But if it's in time, if you're working with a time volume and you want to view that as a backdrop on your cross section, you're going to convert it to depth using the active velocity model. Also within this application, so if I switch back to my active version, I'm going to turn on my 2D seismic as well, and my fault and my horizon, because this next step is actually very useful and interesting, because once you have your velocity model set up, you can also from the 3D view switch your entire scene, your entire time scene to depth. So we have this mode that we call the depth mode. You click on this, and that's going to take the active velocity model, because you can have more than one velocity model, so you can choose which velocity model you want to be active, right here from this drop down, choose from, you can have 3, 4, 5, 10, 15 models, and you can just make one of them active. And then we're going to use the active model, and we're going to convert everything in your scene to depth. So now I'm looking at this 2D line, this section that I have, even this cross line, if I open it up, that's been depth converted, and that's what you're looking at. So even as I navigate this, it's going to be computed, converted to depth using my active velocity model right here, TT2, and display it here. The horizons and faults as well. So if I navigate this somewhere where it intersects with the fault, there's my fault. So these as well have been converted to depth, but they have been forced into intersection mode because we want to keep it in real time. We don't want to spend, and if you're taking that entire, you can have 10, 15 horizons in the scene, and when you switch to depth mode, if we keep them as surfaces, we're going to have to compute the depth surface for each horizon, which can take a bit of time, and then the real-time thing doesn't really hold anymore. So what we do is we keep the horizon in the scene, but we force them into intersection mode, so you can still see what that horizon is doing relative to the seismic in the depth domain, without having to spend that extra time computing the entire surface for the horizon. And as I navigate my seismic, so as I move it, forwards and backwards, these intersections are also updated so that they're always showing me what the horizon is doing in terms of that. So we force them into intersection mode, but they're still showing you the information that you might that you're trying to get from them. All right, now I'm going to switch back to my time mode. All right, one more thing, one final thing with visualization before we get on to our horizon fault interpretation is our voxel rendering. That's the biggest advantage in my view of having a 3D view, is that you can view structures in the 3-dimensional sense. I'm going to open a new 3D view. Like I said, we can do multiple 3D views, and I'm going to now add a probe to the scene. A probe is basically just a cube of data. So I'm going to define my probe here. Let's make it 100 to 450 and 50 to 1200. In the time, I'm going to do it like 300 to 900. Click on add, and that's going to add that probe to my scene. Now I have this probe added to my scene. Probe, like I mentioned, is basically just a cube of data, and it's like any other section that you have, except that it has data on 6 sides. So it's a combination of actually 6 sections, 2 time slices on the top and bottom, and 2 inlines front and back, and 2 cross lines on the kind of like the sides. So just like any other section, I can change data versions on it. So now, for example, I'm looking at this cube from the average energy volume with data displayed on all 6 sides. But if I zoom into it, by definition, this has no data on the inside. It's just data on the walls and the ceiling and the floor, but nothing on the inside. It's like an empty box. To fill this up with data, I can use this render volume option up here. Click on this. It's just now going to read data from the cube, the average energy cube, and stuff it into this box. And just to show that we have data in here, now if I try to zoom in, instead of entering that empty box, I bump into data, and I can't really see that room anymore, that empty box from the inside. I can't see it because it's filled up with data, so you can't see it. You bump into data and you can't see anything else. So what's the advantage of having a volume visualized? Well, number one, for example, this big bright spot, or these 2 bright spots that you see, if you want to analyze them further, now because all of my data is available right here on my GPU, the GPU is responsible for rendering these options for this display that you see happens on the GPU. And I've taken when I render a volume, I've taken my data and not even put it in RAM. I've actually taken it a step closer, and I've put it on the GPU itself, in the memory, chips of the GPU itself. So when I navigate this volume, it becomes much faster. So take a look at this bright spot, and as I move my section, you can see exactly how it sort of is increasing in size and then sort of decreasing, right? There you see it, where it dies out, where it widens, where it splits, and all that. So it gives you a very easy way to analyze what that structure is doing, as it extends into the volume, where it pinches out, where it thickens, where it thins, where it splits, all that information. If I turn off this render volume option, so if I take this data and I discard it, so now I'm back to my empty cube right here, and I try to do the same thing, I can do the same thing, but you can see that I have to move very slowly. So I have to make sure that I move this slowly, and it's going to give me the same effect, but it takes a lot longer for it to navigate. So it's not as natural or as easy to view this. You can still do it, but putting it on the GPU makes it so much faster. So I'm going to render volume again. So that's one way. The other way is to use what we call selective transparency. So if I bring up my histogram is basically giving me the data distribution for any section that I have selected. You can show it right here. It also serves as an advanced color palette tool. So you can change your color palettes here. You can adjust the min and max. The min and max is basically your color range, defines your color range. So anything that falls to the left of this blue line, this vertical line, this maximum line will be assigned highest color available in the color palette, which happens to be this dark blue. Anything that falls to the left of this minimum line or the minimum value is going to be assigned. Anything to the left of this line is going to be assigned the lowest color in the color palette, which is this bright red. So I can interact with the histogram to set my color ranges. But most importantly, for voxel rendering, I can make certain amplitudes transparent. So I can play with this color palette using these buttons up here. Because I'm interested in this big bright spot, which is a high average energy area, what I'm going to do is I'm going to only leave higher amplitudes as opaque and make everything else lower amplitudes. I can make them transparent. So when I use this button, I can adjust this threshold, holding the control key down. I can bring this here. So what I've essentially done is that I've told my display that you can use the rainbow color palette, but modify this color palette so that any amplitude that falls along this portion right here, if you look at the bottom left of my screen, anything that falls on this portion, make it transparent, and only keep amplitudes or values that fall to the left of this vertical green line as opaque. Now, because I have the volume rendered and everything else I've made transparent, I'm only left with these areas these amplitudes that I was actually interested in analyzing, and then you can see that as the structure in here. So that gives you an even better way to analyze your structures. And you can also pick this structure, save it as a geobody, which we're going to get to a little bit later on in the presentation. So that's how you can sort of render voxels and visualize. So we have very powerful visualization tools, and that then enable you to do perform the basic objectives of your seismic interpretation, which would be to map your horizons, calculate attributes on them, mark your faults, have sort of a structured framework for your area on what your subsurface is doing in terms of horizons, faults, and even geobodies. So how do we go about picking horizons? Well, before we do that, let's just remove everything that I have in this scene. I'm going to remove everything else, just keep this one section. And I'm going to add some wells, because one of the first things that you want to do when you are about to pick horizons is to create a synthetic trace. So you want to create your synthetic, and then once you have a synthetic, that means you can tie your well and your seismic and go about from picking this. So how do we create synthetics? We have a very versatile tool again for creating synthetics. All you need to do is anywhere in the application, the map view, the 3D view, seismic sections, wherever you are, just right-click on a well and say create or edit synthetic. You're going to see a data selector of sorts that comes up that says, do you want to create a new synthetic, or do you already have a synthetic that you want to edit? Let's say I want to create a new one. Then I'm going to choose my input logs, my sonic log. Which sonic log do I want to use? If you have aliasing set up in your petrophysics application, so GVERSE Petrophysics is our petrophysics application. If you have aliasing set up, and by aliasing I mean if you have certain mnemonics that you want to use, and but for example you have like a DT_3 for one well, and but when you say, you can define the aliasing which says when I say DT, go to this well and look up the DT curves in there, and DT3 should be given the highest priority. If you don't find DT3, use DT2 or whatever. So you can set up your own hierarchy of aliasing. And when I say DT, it's going to go then and find or auto-resolve that curve and find that for me. So we select those by default, but you can select any one. So if you want to use DT1 or you want DT or any other well that you have calibrated well, whatever you want to use, you can use that here. Same thing for density. We default to row B if you have that. If not, you can come here and choose anything. You can also say, because density curves are typically not very reliable for synthetic work, so you can choose to completely ignore it by saying none. So I don't want a density curve, I want to assume a constant density. You can do that here as well. If you want to estimate that, just go to the estimator, and using the Gardner's equation, you can estimate your density curve from your sonic curve and choose to use that instead. Same thing for your sonic. You must have a sonic curve, so you cannot use the none option when you for the sonic curve. But if you don't have a sonic curve and you still want to create a synthetic, you can use the estimation window to estimate the sonic curve from the density curve using the Gardner's equation. The next section is your seismic selection. Now, the seismic selection is basically for the traces you want to send over, so you can compare your synthetic to those seismic, because that's the objective of creating the synthetic. In this case, to be able to tie your well data and your seismic data. So what seismic traces you want to compare your synthetic to, you can choose them over here. Any volume in your 3D survey, any 2D line that you have. You also have full control over which traces, the actual traces you want to set. So you can use this number traces option. It will put the well trace in the middle, take 12 traces to the right and 12 traces to the left, because my total traces count is 25, and then I'm going to use those traces from the crossline number, inline number, and even the trace number show up here for whichever volume that you have selected, even for 2D lines. So if I select this 2D line, it gives me where this well is being projected in terms of SP, CMP, what the trace number is. So you can either put the trace in the middle, or if you are working in, for example, a faulted area and you don't want to use traces to the left of the fault, you only want to use traces to the right of the fault, go to the trace range option, and that's going to let you graphically or by typing in, let you choose which traces you want to use. And this well location shows up here, so you know exactly where you are. So you say, okay, I only want traces to the right of this well, ignore everything else. So that's how you can choose your seismic. Once you've selected your seismic, I'm just going to use the cross line with 25 traces. Click open SynView, and that's going to launch the SynView window. The SynView is our synthetic editor, which is shown up here now, and it gives you these different tracks where you have your sonic curve, your density curve, the reflectivity computed using the sonic and curve, and then this reflectivity convolved with this wavelet in the bottom left to get your synthetic. Each of these tracks is customizable, so I can go to the synthetic menu and I can say if you want to change your colors, if you want to change the color of the wiggles, do you want to see colors, wiggles, or a color palette, or both. So you can choose all of these options here. Do you want to show it overlay on the seismic or not? Apply a gain to it. So if you're synthetic, like in my case, the synthetic peaks and troughs are not very clearly visible. So maybe want to increase the gain to 9 so that I can see these peaks and troughs better. So you can play with all these settings here, and each track gets its own. Same thing for seismic. I can choose whether I want to see wiggles, color palette, both, what color palette I want to use on it. Do I want to flip my traces? If it's a deviated well, do you want to show the deviation, or you want to work with this, sort of assume a straight well? All of that information you can come in here and you can configure and you can play with. Same thing for these tracks. So I can fill or no fill, which color palette I want to use, the color of the line, thickness, all that information I can adjust. The synthetic parameter lets me, if you want to change your input curves, or if you want to apply basic processing on there. So if you want to say, okay, my DD curve is sort of too spiky, I want to smooth it. So just go to your despiking algorithm, define an operator length, make it really big, so you can actually see the effect, and that's going to then take your sonic curve and it's going to smooth it. And if this is what you want to use for your synthetic, just say save, and that's going to then be used for your synthetic creation. If you want to do a blocking on it, so if you want to not be smooth it, but just say, okay, I want a minimum thickness of 5, maximum layers, let's say I want 20 layers, I'll run process, and then that's going to take my sonic and it's going to block it into these. So it's going to get rid of that high resolution information that these well logs have, and it's going to try to block the curve into certain just given these parameters. And if you want to use that, you can go ahead and use that. Same thing for your density curves. You can apply that same processing steps on your density curves as well. You can also calibrate your sonic curve. So if you don't trust your sonic curve all that much, you have a TD table that you think is more reliable, you can take your sonic curve and you can calibrate it with that more reliable check shot that you have, and that's going to then create a new sonic curve for you, calibrated sonic curve that you can then use in your synthetic creation. For wavelets, of course, the next step is the wavelets. We have these analytical wavelets that you can use, Ricker, Clodder, trapezoid, Butterworth. You can choose these. You can configure this so that it matches your data more precisely to view this seismic spectrum or the power spectrum of your seismic. So you can choose a better wavelet. Just select this power seismic spectrum option, select an area in your seismic, and that's going to give you a power spectrum for that region that you just selected, and you can see how well or poorly your wavelet corresponds to that, and adjust the parameters to get it to match more closely. But for a lot of synthetic work, you don't rely on analytical wavelets. You want to use wavelets from the seismic data itself. You can extract wavelets from seismic as well. You can either extract it from the traces you have displayed over here, that's display traces option, or you can just say, okay, I want to take the entire cube, subset in an inline cross-line direction, even the time range. So if you have like a zone of interest that you want your synthetic to be perfectly matched in, you can say, okay, for these 500 milliseconds, extract a wavelet from the entire seismic cube, and that's going to then extract that wavelet from the cube and display that over here. If you save it, it's going to then be used to create my synthetic. You can also sort of limit your extraction around the well location, create as many wavelets as you want. These are saved at the project level, so cross interpretations, you can share them very, very easily as well. So once you have your wavelets and you want to now edit your synthetic, make sure that it ties well, that's the well seismic tie ribbon. You can apply a bulk shift. So if you say, okay, I want to make sure that this peak sort of lines up over here, double click, and that's going to take the entire synthetic, apply a bulk shift to it. If you want to do a stretch and squeeze and say, okay, I'm happy with this peak being here, but I think this particular peak should actually go down here. And you can do that. We have like a drift curve and interval velocity curve as well to help QC these changes that you make, so that you maybe not do something too crazy. We also have a correlation which takes your seismic trace and your synthetic trace, gives you a correlation score, how similar they are to each other. You can also auto compute the best time and phase shift to apply to get the maximum correlation, and update your synthetic to match that as well. You have full undo redo capability, so you can go in here and undo this, set the phase to 0 as well. Auto multi-point align that lets you choose multiple peaks. Instead of doing it one at a time, you can say, okay, this peak maybe goes here, this peak maybe goes here. I think this one should be down here. Let's put this one down here, double click, and that's going to then take that entire synthetic. Instead of doing it one by one, it's going to take that entire synthetic and adjust it. Now, once you're happy with everything that you have, you can commit this and save that as a synthetic. I'm just going to call it Syn2, for example, and add it as a new survey. So each well can have multiple synthetics in there as well. And now I have that synthetic created, and I can use that to start picking my horizons. All right, so let's go back here for this well. What I'm going to do is I'm going to go to my display settings, because we have several display settings that you can use to post information along this well. So I can say, okay, I want to go in and I want to see all the formation tops that are available with this well. That's my formation tops for this well. Let's make the font a little bigger so you can see it more clearly. Let's make the size larger as well. If you want to annotate your MD with it, the source that actually picked this formations, the observation numbers, you have all that information available. And you can also go in and modify these picks, because we are fully integrated. You can go to the well tops menu, say adjust a pick, and you say, okay, maybe this pick should be up here or down here, and that's going to be then updated again into the database so that anybody else with that pick can see the modified pick as well. I'm going to open maybe a cross line right through here along the well location, and let's say you've done you've gone in and you've displayed your formation. Let's turn on the synthetic curve as well. So I'm going to go in here and say synthetic. That's going to show me my synthetic curve. So we've done our analysis, we have the formations drawn along the wellbore, we have the synthetic display here, and you've identified this particular horizon going right through here, and you want to start picking it. Anything you want to do with horizons, go to the Horizons tab. This is where everything that you want to do with horizons lives. We have certain advanced workflows as well, but for this presentation, I'm just limited to the basic horizon interpretation, basic horizon picking. First thing you want to do is maybe create a new horizon. Let's call it H1. You give it a color and give it bright yellow, so it's easy to spot which event you want to detect. So right now I'm looking at this peak, this black peak, and I want to pick this. So just say event detection is peak if you want to associate a formation with it. Guide window, the window in which you want your horizon to be tracked. If you don't find a peak, which is my event detection setting, within this guide window, we're going to skip that trace and stop the picking. All right, so we have other parameters as well, of course. A lot of other parameters called advanced parameters, these correlation tracking, what you want to do when you hit a fault, all that information you can also configure. Once you're ready, hit create, and that's going to create that horizon. And you must be sure to set it as the active horizon. The active horizon is the one that's going to get your picks. The picks that you make are going to go into the active horizon. We have a bunch of modes to help you pick your horizons, both in the Seismic section, the traditional interpretation view, or the 3D view. So you can go in here and say, okay, I want to do a polygon pick, which is basically you tracing in a series of clicks the interface you want to pick, double click to commit, and that's going to then snap those picks to the nearest peak, which was my event detection setting, and pick it. So you can go on and, sorry, I'm just going to hide this for now, right, remove it. So you can go ahead and you can start, keep doing this manual picking, or you can use the 2D auto pick mode. That's going to, with a single click, you can then pick the horizon for the entire section. Now, the one big advantage I find of picking in 3D view is the fact that you can now very easily right-click here, say I want to open an inline over here. That's going to open this inline, and you can very quickly see where this horizon is intersecting this particular interface, and then very, very easily mark this pick. We also have a project feature. So if I turn this projection on, that will project my horizon onto unpicked sections up to 10 lines. So if I navigate this this particular inline that I just picked on, if I navigate it, 10 inlines forward, so now you can see this dotted line is basically a projection of my horizon. It's telling me, okay, based on the picks that you've already made, this is the interface you're probably looking to pick. Again, a very useful aid in making these picks, and this is also available in the seismic view. So if I view this same section in the 2D view, so this is my my 2D view, and if I scroll down to the position where I'm trying to pick this horizon at, this is the particular horizon that I'm trying to pick. So you can see that this comes up as a dotted line in the 2D view as well. So then you can go in and you can pick it over here or in the 3D scene, and you can make all these picks. Let's add these picks over here in the 2D view, and then you can also see on your main map view. If I switch to my main map view, this horizon is being added into the map, and you're getting these picks. Now these are my seed picks, and what I call my seed picks. You can use these seed picks to then go in. So I have picked it only on a couple of inlines and a cross line. Ideally, I will want to pick more, but I can go in and then I can run my auto tracker. I can say, okay, use these picks that I've already made as my seed picks and run the auto tracker to then spread this horizon across my survey. Runs the auto tracker. It comes up with this horizon surface that I can see over here now. That's my horizon surface. And of course, because it's a correlation algorithm, it's got some empty spaces in there. You can go in and you can QC it, put your line there, see where you want to put it, put your picks there, or you can use our fill gaps option to fill these, interpolate between these small gaps that are left behind, and sort of get a much more smoother looking horizon. So it doesn't fill all gaps because we define a gap as something that has picks on all sides. So any open areas are sort of left open, and we don't fill them out. But you get this horizon coming in. Now, if you want to QC your horizon, you can do a bunch of maps on it. Just like for my seismic sections, I can click on this little label list to display many different things on here. If I have gridded velocities along this horizon, I can view that data. If I have depth values gridded for this horizon, I can view that over here. You can look at data from seismic volumes on it here as well. But for your picking, QC of your picking, you can look at different pick attributes. So I can look at my pick type, which is where are my manual picks, where are my, so I'm going to hide my seismic sections. Where are my, these blue are my manual picks, reds are my auto picks, so you can see what your tracker has picked and what you've actually picked manually. You can look at your pick order. How did the tracker go about making these picks? You know, the map. And if I turn on my color bar, you can see blues are the late picks and reds are my earlier picks, starting with my seed picks. But perhaps most importantly, you can look at the confidence you have in your picks. Now, as the picker goes on, it assigns a confidence value to each pick that we make, and that's what you're looking at here. And you can manipulate your display based on these pick parameters as well. So you can open my pick attributes panel right here, stock it down here, and say, okay, I just want to see picks that have at least 70% confidence. My picker has at least 70% confidence. So you're now left with picks that your picker is at least 70% confident. If these are the only picks you want to use, and you want to maybe loosen your picking criteria and run the auto tracker again, or go in and pick everything else manually, you can discard the picks that you don't see. So now my horizon is going to be left with just those picks, you know, the picks with at least 70% confidence. Even if I set this value back to 0, so I want to look at all my picks, you won't see them because they're now deleted, they're gone from that horizon. We of course have undo redo functionality, so if you feel free to play around with these, because you can always, you know, with a single click of a button, bring everything back. So if I undo it, everything is going to come back and be displayed. Now, one last thing that I want to show you is a pick path, where you can select a pick. Zoom in a little bit more and pick this one. That's the next one. So what's happening here is that it's showing me, for the selected pick, it's showing me the path that actually led to the picking of this pick. So which picks contributed to this pick, this blue pick being actually selected and picked. And then the purple shade is telling me all the picks that were, you know, this pick contributed to picking. So the child picks for that particular pick. And the advantage of having this is that if your tracker has jumped up and down a little, of course, garbage in, garbage out. So instead of having to create this complex polygon trying to, you know, delete the bad picks, you just select this pick, say discard, and that's going to discard all the subsequent picks that sort of were generated because of that one bad pick. And that's going to sort of remove those picks from your horizon. Again, you can undo to bring them back. So that's how you're going to very quickly QC your thing, create confidence maps, pick order maps, these pick relationship displays to very quickly see how well your horizon was picked and adjust those picks to make sure that the horizon is doing what you expect it to do, what you want it to do. All right, so once you have your horizon, you know, you can create time maps for it. So you can create velocities along it. To the main map view, of course, this is that same horizon displayed in the main map view. You can grid velocities on it, convert it to depth. You can compute attributes on it. So from the attribute calculator, attribute service calculator, you can choose from all these different attributes, and you can either do a window about the horizon. So you can say, okay, I want to do the RMS amplitude. Maybe I want to do the total absolute amplitude for this new horizon that I just picked, and that's going to then calculate these attributes in a window about that horizon, the length of which you can set here, and that's going to display them. So let's say I want to do it in a 10 millisecond window, hit calculate, and that's going to then calculate those two attribute surfaces. We call them attribute surfaces for the RMS amplitude and the total amplitude, total absolute amplitude, which I've selected here. But I could select from any of these. I could even do an isochron thickness between two horizons. But so it's given me that window and those attribute surfaces along that window. The window itself can be between two horizons. It can be between two, you know, fixed times, or even at within a geobody. So if you have a geobody, you can actually say, I want to extract these attributes within this geobody only. So that's how you calculate attributes. You can do horizon math here as well, so you can define your own expressions for different horizons, add them, remove them, multiply them with surfaces. We have like a 2D horizon calculator, 2D attribute surface calculator. So if you picture horizon on 2D data, you can do the same thing. We also do some basic curvature and geometric attributes that you can perform along the horizon over here as well. So a pretty rich attribute library that then creates those maps, and you can view those maps. So I'm just going to double click it from this tree, and it's going to show up here. This, of course, you can also view in your 3D view, these attribute surfaces. One of the most important outputs of any interpretation, you can view them in the 3D view as well. All right, so that's horizon picking. Let's now move on to some fault picking. I'm going to open up a new 3D view. So we have a blank window here, and let's add a seismic section here. Anything will do. For the next set. All right, so I have a section here, and I'm going to try to find a nice fault for you guys to pick. There it is. That's a big fault going right through here. So how do we go about picking it? The fault workflow follows the horizon workflow very closely, but it's a lot simpler. So you go to the faults menu, you say, okay, I want to create a new fault. Let's call it F1. Oh, I already have a fault at F1, so I'm going to call it F4. Give it a color. Let's call it a bright green color. Hit create. With faults, there are nowhere near as many parameters associated with it, so we don't have that more parameters option. You create a fault, and then you can go in, make sure that it's the active fault, and then start picking it. So you can see this fault right over here, and I'm just going to start to pick it. Double click to commit, and that's one fault stick right there. Navigate my section. Let's say I want to go 10 inlines in this direction. Pick this fault right here. Navigate more. If you want to do the fault same as horizon, if you want to project your fault so you can see where that fault is lying, if you're working in a very heavily faulted area with faults very close to one another, you can turn on the projection, and that's going to guide you where that fault might be. And as you make your picks, your surface starts to form, and you get this triangulation between in there, and that's basically how you go and pick your faults. I'm just going to hide this, or actually remove this. Now, once you have your fault, and I'm just going to pick 3, but this fault is a pretty big one. It goes quite far across. But you can go in and you can edit these segments as well. So let's say I want to look at this one, and I don't like this bend that I have going here. So I can right-click here and say fault segments, edit fault segment. It's going to add that section that I picked this fault on. Even if it was an R line, it would have recreated that R line, and then I can adjust this fault to get rid of that bend, maybe add nodes, move nodes, and all that stuff. Again, undo, redo, everything that you do with this fault is available in the undo, redo menu. And the way we do undo, redo is that if you, whatever fault you have is active, the stack sort of this fault, this undo, redo history is available for that particular fault. So if I switch this to F2, for example, this undo, redo stack goes away because I've made no edits for the fault F2, so there are no undo, redo steps in there. But when I go back to F4, it shows me the steps that I made for F4. So if you're picking 2, 3, 4 faults at the same time on same sections, you don't have to worry about, and you made a mistake, you want to undo. It's always going to undo the last step for the active fault. It's going to leave all the other faults alone, even if that was the exact last step. Chronology speaking, if that was the last pick that you made. All right, so that's how you pick faults. Pretty easy, pretty simple. We've also added automatic fault extraction. That's shown here in this menu. Automatic faults work by actually, you first have to create a volume. Sorry, wrong button. You have to create a volume. This is where we encode fault information into volume. This is a one-time process. You create this fault volume. You can use it in different interpretations as well. So you just have to create this once for each sort of amplitude volume that you want to pick faults on. Once you have it, you go in and you link this volume. So I want to say, this is me telling my system that for my F3 original survey, I want to pick faults using the F3 block original.afb file. That's the file I created in the last time. I link that, and now we have a couple of modes, the segment pick mode and the surface pick mode. The segment pick mode, what you would do is just turn it on. I'm going to switch to fault F2 because you have to make sure that you're picking into the right fault. Click on segment pick, and what you're going to see is these red lines show up. These are showing you where we think all those faults are. And as I navigate my section, this will update to show me where the system thinks the fault volume found all those faults. If you like what you see, maybe this is the fault you want to pick, just click on it. And because we're in a segment pick mode, it's going to follow this red line and add a segment to it. And that's my segment added. So you can see it's added one segment for that fault. I can navigate this further. So I can say, okay, for this inline, I want to now move 10 inlines in that direction. It's going to do the same thing. You can see that here, click on it, and that's going to add a segment for this fault, and I'm going to start to see my fault surface. My projection turned on, so I can see this fault projection coming up here again, because I'm in the automatic pick mode. So these red lines are not actual interpreted faults. These are just sort of there to tell you that the fault volume thinks there's faults there, and then you click on it to accept it and add it as a segment. Now, once it's added as a segment, it works as any regular segment. You can go in and you can say, okay, I want to right click here and I want to edit this segment because I don't like the algorithm sort of making the fault bend over on itself. So maybe this node needs to move here. Same thing for this one. Again, right click here, say fault segments, move to the previous segment. That's going to jump the section over here, and then I can go in and maybe delete this node. Fault segments, remove fault node, and maybe move this node down here. So you can go in and you can make this is sort of helping, instead of having to trace that entire file, the entire fault, you can just then choose which segment you want to edit, which parts of the segment you want to edit, and make that fault. So that's our segment pick mode. We also have what we call a surface pick mode, that instead of doing this segment by segment, it picks the entire faults. Again, I'm going to switch my faults active fault to F3, go to my surface pick mode this time. The workflow is the same. It's going to show up as these lines that come up here, and then I just pick one of them, let's say right here, and pick, and that's going to then, instead of having to going segment by segment, it's pick that entire fault surface, go through the volume, find that fault, and it's going to pick that as the entire fault surface. And there's my fault. It's a pretty big one. So you can go in and you can do this, segment by segment or surface by surface. And again, the undo redo functionality that I was talking about, a little easier to see here because this is for my F3. I did an surface pick. You can see undo. It says automatic surface added. From if I undo it, the surface is going to go away completely. If I redo it, it's going to show back up for the F3 fault. But if I switch this to F4, which was the one I was picking manually, you can see the editing steps are now for the fault F4. So the undo redo list is context sensitive. It knows exactly the fault that you're talking about. So undo, and for the horizon picking, the undo redo functionality works in the exact same way. Now, for one last thing before we move on to Geobody picking, is the bulk picking for your faults. So this is fine, good. You can pick your faults automatically, segment by segment. You can do it surface by surface. What if you want to go in and you want to get a first quick look of what your faults are looking like in that entire cube? Instead of having to go in and pick your faults one by one, you can go to the bulk pick option. Here you can then choose, let me open a time slice here, so that will help us choose the region that we might be interested in picking. I'm going to switch this to the semblance version again because faults show up really nicely on semblance data. So let's say I'm looking at this heavily faulted area right down here, and I want to do a quick bulk pick to pick up all these faults. Indicated in red. They're indicated in red because I have my surface pick mode turned on. I've turned it off. It's going to go away. So let's say I want to maybe from cross line 400 to 600, 700, and inline 400. So in this area, I want to pick all these faults. So I can go in and do bulk pick, and I'll say inline 100 to, let's go 400. Cross line range from 300. I'm going to do 600 because I don't want to take a lot of time. Time range also, I'm going to go, because we are very quite far down in our surveys, I'm going to do 1500 milliseconds to the full extent of the survey. Minimum height of the faults to pick is 50 milliseconds, and hit start. Now, this is going through my volume, picking all the faults, and creating fault surfaces for them. But we don't just create fault surfaces and add them to your interpretation without giving you a chance to actually look at them and analyze them. So what we do is we actually create what we call temporary faults. So the result of this bulk pick is going to be a set of temporary faults that you can then view in a scene, just like your regular faults, but you can't really do much with them except look at them in relation to your seismic, in relation to everything else that you have, horizons of the faults, and then decide which ones you want to actually convert to your interpretation. And convert to interpreted faults. It's going to be done in a second, and that's what I mean. So it's picked 261 faults, which is added to a new view that we call the fault view, and there's all my faults. Let's open that time slice in here as well, the one that we used to identify area. I'm just going to copy it to fault view. And there's my time slice, and you can see it's done a pretty reasonable job of picking up all those faults. We have some faults here that maybe we don't really want to need. All right, so now we can, and you can see this show up as temporary faults. Now we can go in and we can see which faults we want to keep. The rows diagram is a pretty helpful thing in that. And now I come up here, let's say I'm only interested in these north south running faults. I'm not really interested in everything else because the rows diagram is giving me the azimuth of these faults as the compass direction and the tip of these faults as the length of these petals. So I can say, okay, I just want maybe the north south running faults. I don't want really anything else. It's interactive. So as I select this, it just shows me the faults that are left here. These are the only ones I want to work with. I don't need anything else, so I can then use the delete option to delete this. But if I delete this right now, it's going to delete my faults that I actually want to keep. So what I'm going to do is invert my selection. That shows me everything else, things that I don't want. Hit delete, and that's going to remove these 212 temp faults from the scene altogether. Now, if I select all, these are just the temp faults that I'm left with. Next, maybe you don't really want these small faults in there as well, so you can go to your fault view, say multi-select, and select the faults that you don't need. These 3, 4, 5. I don't need these, so I say delete, and that's going to delete these selected files as well. Similarly, this fault has been picked up as 2 separate faults. Maybe you want to keep them as a single fault, so select them and say merge, and that's going to merge those 2 faults or 3 faults, however many you selected with a single fault. Now, if you're happy with this fault, you can go in here and you can say convert, and that's going to take this fault and it's going to convert that fault into an actual fault, into a interpreted fault, and you can see this shows up as this, in a separate category called fault. Very quick way to help you cut through the clutter and from your automatic faults that you have, convert them to accurate interpreted faults that you can then use in your workflows. So that in a nutshell is how automatic fault extraction works within GVERSE Geophysics. All right, so the last thing that I want to show you today as far as interpretation is concerned is picking geobodies. And if you jog your memory back to when we started this session, which was just about an hour ago, I showed you how you could isolate structures in the 3D view to view these as geobodies. So how do you go about picking them, saving them in your interpretation as a geobody, and then what can you do with those geobodies in terms of your interpretation? What value do they add to your interpretation? So what I'm going to do is, again, open a new 3D view, just so that I have less clutter. I'm going to add a seismic section to it from the average energy cube, because that's where that bright spot that I showed you earlier is going to show up. So that's going to add that section here. So this is that bright spot that we have displayed here as a sort of voxel rendered structure. And I want to pick this now. So workflow again is the same. From the geobodies ribbon, create a new geobody. Let's call it G1, and I'm going to give it red color. Hit create. I want to make sure that it's set as the active geobody. It is the only geobody available right now. Set as active, and then you mark your seed clicks. So you can go either create a polygon, so I can isolate my area using the polygon, right? Or I can use a brush mode, which I can then paint over this area, just like Microsoft Paint, and say, okay, this is the area that I'm interested in picking. You can afford to be a little sloppy with this because we have a couple of modes that let you pick geobodies. You could either go in here and do this section by section, and then interpolate these picks to get your geobody, or you can track this signature, the signature that we're picking. You can track this signature. I'm just going to undo all those picks that I made. So you can track the signature through the volume. Go to generate. Choose tracking as your method of generating the geobody. If you want to subset it, you can. If you want to limit it between two horizons or between two time values, you can. It gives you a histogram of all the data distribution of the seed picks that you have. So you can see that this is just the distribution for the data that falls under those seed picks. Because I'm only interested in looking at high average energy areas, I'm just going to go as far to the right as possible. And now, because I was sloppy, so I included some low average energy amplitudes in these seed picks as well. So I'm going to adjust the minimum threshold so that I just have the high energy areas isolated here. Hit generate, and what it's going to do is it's going to take your seed picks. It's going to apply this amplitude threshold to each pick in those seed picks. If it meets the criteria, it's going to be made part of the geobody. If it doesn't, it's going to be ignored. And if it does make it into the geobody, you're then going to check all the neighboring samples in all 6 directions, right, left, front, back, up, down, to see if the neighboring samples, which of these neighboring samples match that amplitude threshold criteria that you defined as well. If that matches, it's going to be added, and so on and so forth, until we find a sample that has no neighbors which fall into this amplitude threshold that you define. That's where the geobody tracking ends. So that's what you get. This is that geobody that we just picked. I'm going to hide this section so you can actually get a view of this. And if you can see the 3D structure right here, it's pretty close match from what we picked. And if I copy this here, so if I copy this to that 3D view and then toggle this geobody, you're going to see how perfectly it matches. And so that's how it didn't pick this part as the geobody because there's no connection between them. It found this sort of link between the two bodies and then picked it. So that's how you're going to go and pick this structure, save it as a geobody. We also have another mode called the interpolation mode, which is also very useful in certain situations, especially when you're working with channels. So let me open another time slice, this time from the semblance volume. 40 is a good one. I'm going to add that time slice. And on that time slice, there is a channel system going right through here. You can see this channel system going right through here, shows up really nicely in my semblance volumes. And now I can pick this channel system as a geobody as well. To do that, again, I'm going to create a new geobody. Sorry, I'm going to go here, let's call it Chan for channel and give it a yellow color so it stands out. Hit create, make sure it's set as the active geobody. Go to brush pick mode and let's pick this channel right here. Just paint right over it. If you don't like this, you can edit the seeds and you can adjust the thickness as well for this because I'm using a very thick sort of brush size. There's my channel pick. Again, go to brush mode and pick this second part as well as a channel. Let's navigate upwards 10 milliseconds. Find that same channel and make these picks as well. I'm going to do it really quickly because I think I'm about to run out of time. I do want to take some of your questions as well. Move up here and let's keep going. Let's make this one last pick and this. Maybe I'll pick one more. Again, I'm just being very sloppy with these picks. If you're actually doing this for an integration workflow, you'd be a little more careful. So once you have all of these picks, you then go to generate. Now, instead of tracking my signature, because I was picking on a semblance volume, my picks pretty much cover the entire data range that I have available for the volume. So tracking is not really going to help because it's going to end up creating an entire cube geobody for the entire cube of size. And in fact, it's going to be I'm pretty sure it's going to be so big that we won't be able to handle it. And we're just going to stop midway and tell you that this geobody is way too big for us to generate. So what you can do is you can interpolate these picks. Go here, say interpolate, hit generate. It's going to take those picks and it's going to generate a geobody by interpolating those picks. I'm going to hide this here, and that's my channel. Again, I was very sloppy with my picks, so you see these are a little all over the place. Because with interpolation, you can't afford to be as sloppy as we were when we were generating this bright spot geobody, because we were defining an amplitude threshold, so we could afford to be sloppy because we had a mechanism to exclude unwanted amplitudes. But when you're interpolating, we take your picks as is, as they are, and then we interpolate them to get you. But this gives you like a geobody for that channel you had. So what can you do with this? Well, number one, you can map thicknesses for these geobodies. So I can just say right-click here and say copy to, let's say, a new map view, and that's going to add a new map view window to the 3D view, and it's going to show me this channel as thickness of this channel. You can do gross thickness, you can net thickness. You can look at the time structure map for the top of that geobody, so you can see it's a very gradual sort of getting deeper gradually. Let me turn on my color bar so you know exactly what these values mean. Blues are your shallow times, red are your deeper times. You can see sort of gets deeper as it moves towards the southwest. Same thing for your base. The base seems to get deeper much quicker, much more rapidly. And so you're looking at the time structure map for the base of your geobody. So you can do these maps. You can create layers for them. You can right-click here and say I want to create an isomap layer. An isomap layer is, and you can create layers for everything. You create layers for horizons, for faults, and that gives you a layer that you can then bring onto your GeoAtlas maps or geology tools or anywhere else, you know, outside this GVERSE geophysics application, the GVERSE geophysics domain. If you want to use these time structure maps, these depth structure maps, thickness maps, if you want to use them in other workflows, in external apps, in GeoGraphix, you can create these layers and take the data points with it, take the grid with it. You can regrid these values in GeoAtlas as well. You can also, like I showed you earlier, you can also use the attributes and surface calculator to compute attributes within geobodies. So the geobodies that I have will show up here, and you can create attribute maps for them as well. You can also do basic volumetrics. So from the geobodies ribbon, I can go in here and I can say volumetric, and that's going to then let me, if I have a suspect lateral variations within the geobody, I can use the active velocity model option, or if I know a representative velocity for my geobody, I can use just that estimated velocity to get a volume for the channel geobody or the G1 geobody, and that's going to give me an estimated volume. And we maintain this list, we save this in the interpretation, so you don't have to sort of jot it down. You can try different velocity values. So for this G1 value, I could even try a 3,000 meters per second value and see, you know, the difference in volume that would create. Because again, I'm in the time domain. To go to the depth domain, I need a velocity value here. If I wasn't working in the depth domain, I wouldn't need this velocities. But like I said, we keep a track of this, and this exclamation mark tells me if something, you know, if the geobody surface has changed from the last time I picked it, which it obviously has because I picked it as a new geobody in this case. So it's giving me a yellow warning that this geobody has changed since the last time we picked it. So these values may not actually mean much, maybe irrelevant. So that's how you go ahead. You can do volumetrics. Another useful option is to convert your geobody to a horizon. So if you want to use the geobody in your velocity model, or you want to do a you know, any other, you just want to do an amplitude extraction along the top of your geobody, not within the geobody. So you can convert it to horizons just with a click of a button, and that's going to take the top surface and the base surface, convert it to horizons, and then you can work with those horizons. So let me go in here and add those horizons that I just created into the scene. So I'm going to go to channel top, channel bottom. From the scene tree, let's hide the geobody itself. So now I'm looking at the two horizons. So this is the top horizon for the channel that I just picked, and this is that base horizon for the channel. Just picked and time values displayed by default. Right, so that's an overview of some of the capabilities that GVERSE geophysics has in terms of seismic interpretation. We talked about how we handle seismic data, which is in terms of surveys, which is the geometric information, and then data versions, which are the actual trace data files, multiple versions of data for each survey. As you saw during the course of this interpretation, there are many different uses for having these different versions. 2D seismic as well. You can also group your 2D lines into programs, and then the 2D line is the geometric information, and then data versions for each 2D line. We looked at some of our visualization capabilities, voxel rendering, then some basic horizon fault and Geobody interpretation workflows. We, of course, have a lot more to offer. We have a full-fledged line balancing tool that lets you balance 2D seismic data. So if you work a lot with 2D data and you want to tie those lines, we have a bulk tool that will do a least square method to compute an overall shift, or you can do an interactive method where you can actually eyeball the thing and modify your data based on what you see, do an auto calculation as well, and then apply those to your line. We save everything in a shifts table. So if I go to the home table, I have a shifts table that lets you configure all this, so you can export and import these values as well. So if you have a different set for your shallow work, a different set for your deeper work, you can very easily import and export those shift values to this table to get to the data that you want quicker. So a synthetic module to tie synthetic traces. We have a new crossplot tool that lets you create crossplots for horizons. We have these advanced workflows where we have ability to snap a horizon to another event. So if you picked a horizon and then apply a phase rotation to your seismic, now the seismic and the horizon are no longer, the horizon is no longer at the correct spot because you picked it on a peak and then you did a phase rotation and you moved the peak, perhaps. So you can take this snap option, which finds the nearest peak or the closest peak above or below the horizon and snaps to it. So you have a lot of control over that. You can smoothen them, you can merge horizons, you can create a surface from the horizon, or you can take a surface and convert it into a horizon to view in your scene. We also have a new facies classification tool that lets you classify waveforms or facies on a horizon surface using the SOM method, the self-organizing maps algorithm. So that's our first AI-based workflow, which does this automatic classification for you. We have, fault polygons that you saw briefly, you can create for horizon as well. Belt-up integration, depth conversion workflow. So a lot of other things that we have that we just didn't have the time to go through.